I'm Costin, and this is joint work with my colleagues at the University Politehnica Bucharest. So the lead author was our student Andrei Croitoru, who is now at Facebook, and he wasn't sure he could come, so that's why I'm presenting it, and my colleague Dragoş Niculescu. All right, so we strongly believe that Wi-Fi mobility is back in fashion, and that's because cellular data is growing at a very fast rate, and existing cellular deployment can't really keep up with the need for data especially in dense urban areas. So offloading to Wi-Fi has long been touted as a good solution, and to back this up, there's a lot of deployment of hotspots in all major cities. And this is a picture from central Bucharest, where we have this cellular provider that is deploying a lot of access points in this square kilometer area. And what's not shown here is there are two other providers that are deploying a similar type of footprint in the same area. So basically, in this area, you could, if you wanted to, only use Wi-Fi even when mobile. The trouble is, Wi-Fi, it's mostly a static connectivity solution, and cellular mobile works, Wi-Fi doesn't. So why is that? Well, the problem with Wi-Fi is that really the mantra of Wi-Fi is to connect to one access point at a time. And then what the client does, it looks, it monitors its signal. When the link fades, for instance, if you see less beacons than a specified threshold, you look for new access points. Once you have a list, then you select one of them and you connect to them. And this is what's called a fast handover, and there's been tons of research into how to optimize this. And a lot of this research has gone into product. So basically, if you have a centralized scheduler that connects all the APs, that you can make this a lot faster. Now actually, a lot of this work is very, very useful, but it doesn't apply to the case where I showed you earlier, where you have uncoordinated access points, and it has another fundamental flaw. The flaw is that you actually don't know the performance of a given AP. You can't reliably predict it until you actually connect to it. And the problem is, even if you did know, when clients are mobile and you have different clients connecting at different times, the best AP for any given client can change very quickly. So even if you could properly select the best AP, you have to change very quickly, and that's something that this one AP at a time philosophy doesn't do very well. So in this work, we're basically taking a step back and saying, why bother selecting the best AP at any point in time? What would happen if you actually connect to all the APs you see at all times, and then you spread traffic with this newly developed multipath TCP protocol that's been already adopted by Apple and implemented on iOS devices? The key to doing this is actually having still a single NIC in the client, so requiring no hardware changes. And it turns out that implementing this is actually straightforward. So for instance, in the Linux kernel, you have support for virtual wireless interfaces, and all you need to do is leverage this support, and you can connect to multiple access points at any point in time. And that's, as I said, it's trivial on a single channel. If you want to connect to APs on different channels, you have to use channel switch support, and there's previous work that shows how to do this. So in a nutshell, this is what we're trying to achieve. A client will see, let's say, 3 access points. It will create one virtual interface for every access point. Each virtual interface will have its own separate MAC. You associate one virtual interface to one access point, and then with multipath TCP, you add one subflow per access point. And now the basic question is, well, how do you split traffic across these access points? Remember, we still have a single NIC, which means you can receive from at most one access point at a time. Okay? So if you think about it a little bit, the answer is, well, most traffic should come via the access point that gives you the best throughput at that point in time, right? So that will be normally the case. It's unlikely that you'll have multiple access points that give you exactly the same throughput. So most of the time, you'll have one access point that's good, and what you really want is to probe the other access points in case you're mobile and the situation changes. You want to be able to detect when another access point becomes the best. So to understand how this works, we basically just took existing software. We built this very simple testbed in our lab. So we have a bunch of Linux-based access points. We have a laptop that acts as a client with a single network interface running multipath TCP. And then we run a number of experiments to sort of understand what the performance is. So we did a lot of experiments on a single channel, so the APs will share the same wireless channel, and on multiple channels. I don't have time to cover the multiple channel experiments, so please have a look at the paper for those. So the first case is when the two access points cannot hear each other, and this case is typically dubbed as the hidden terminal case. So the two access points cannot hear each other, they start sending at the same time, and their packets will collide at the client. So in this figure, what I'm showing you is the throughput the client gets as it moves through our room. So it starts close to access point 1, which is position 1 in the graph on the x-axis, and then the position shows you where in between the APs the client is. So when you're at position 8, you're close to access point 2, and in between somewhere in the middle. And the line I'm showing here is the throughput you get if you only associate to access point 1 and you're using UDP for transport. So basically, as you're close to AP1, you get perfect throughput, and as you move farther away, the throughput drops because the signal fades. The same thing happens if you only connect to access point 2. So basically, you'll get pretty poor throughput when you're far away from the AP and better throughput when you're nearby. And then if you connect to both access points and use UDP, this is what happens. Okay, so there's sort of two sides to this graph. The sides, the two sides basically near the access points, you actually get pretty good performance despite using both access points at the same time. And the reason for this is even if you're decoding a packet from access point 2, which is far away, the minute access point 1 starts sending, it sends at such a higher power that the radio can actually start decoding that packet immediately, and it doesn't waste time, right? So you actually have no collisions because of this capture effect in Wi-Fi, and the throughput you get is close to optimal. Now the problem is here in the middle. So this is the typical example where you get hidden terminal problems. So the two packets coming from the two access points have roughly the same power. So as the client cannot really decode them at the same time, both packets are lost. The two senders back off, and then they try again and so forth. The only reason this doesn't go to 0 is because after many repeated backoffs and randomized weights, at some point one of the APs gets packet in, but you still lose 60% of the throughput. Now, if you just use multipath TCP in the same case, this is what you get. And the case on the edges, I've already explained, but it's kind of funny that in the middle you get near optimal throughput. And what we did is we actually analyzed why this is the case, and I'll give you the gist of it. So basically what's happening is that one subflow is sending at full rate, and the other subflow is completely starved and experiencing timeouts. And on the course of a few tens of seconds, they might flip, and the other subflow might send at full rate, and the other one is starving. There's a full explanation for why that happens in the paper, and the underlying reason is this interaction between the MAC and the multipath TCP protocol, but I don't have time to cover it. So the second case is when you have two access points that can hear each other. So basically, they'll refrain from sending. They're doing carrier sense. And again, you see that multipath TCP traces the optimal line in this particular case very well. So this is an experiment run in 802.11a. So this is in the 5 gigahertz range. Basically, what's happening is, well, in this area, if you look at what's happening is it's ideal if you only receive from access point 1. And this is what's happening, and that's why you get the perfect throughput. But the question is, why are you only receiving from access point 1? Shouldn't you be taking turns and receiving from both access points? So if you look at what happens is, well, you have these two access points that are ready to send. They'll run the contention algorithm. Let's say access point 1 wins. It gets the packet in. Now, what's happening is access point 2, in this particular case, was actually using a very high transmit rate. So the same transmitted as access point 1, so 54 megabits. But it had a much higher physical loss rate. Okay, so this packet would be lost, and this would push access point 2 into a backoff, in which time access point 1 could push a lot of packets. Okay, now access point 2 would actually fail to deliver a packet again and then back off again, and the effect is that the closest access point would actually win the contention most of the time, utilizing the airtime very efficiently. And in the middle, you actually sometimes get a bit more throughput than if you just use any of the two access points, and this is because MPTCP allows you to utilize channel diversity. So, all right, so I've shown you the two basic cases, hidden terminal and carrier sense, and it seems the performance is just great. So are we done here? Can we just use this in the wild? The answer is no. Okay, so when we did experiments with 802.11n, we found that the performance was actually not great, and MPTCP using multiple access points would give you half the throughput you should get if you just use the optimal access point. So to understand why this is the case, again, we looked at what's happening at the MAC layer. So again, access point 1 will win the contention, you send the packet. Now the problem is, in this case, access point 2 was actually utilizing a much lower rate. which had a much better packet delivery ratio, okay? So basically, access point 2 was not backing off. It was sending packets the same, its success rate was the same as access point 1. The problem is by sending at a lower rate, access point 2 was utilizing a lot of airtime, and in effect, these guys were taking turns in utilizing the air, okay? So what you were getting is basically packet level fairness. You know, this is what the Wi-Fi MAC was giving you, and this is why we were actually wasting a lot of throughput. So taking a step back, we noticed that, you know, carrier sense performance depend a lot on the rate control algorithm run by the APs. So for instance, when all the APs use the same bit rate, or they use Minstrel, which is the default rate control algorithm in Linux, which is actually quite aggressive, the performance was near optimal. But when you have less aggressive rate control algorithms, or when you go to using Minstrel HT, which is the rate control algorithm for 11n, what you are getting is actually bad performance, okay? The trouble is, if you want to solve this issue, you could say, well, why don't we fix rate control algorithms? Well, they are really specific to every access point, so you would have to convince all of the access point producers out there to actually change their rate control, and you'd have to update the already installed base, and that's clearly a no-go. So what we are going to do is we're going to attack this problem at a different layer. We're going to use multipath TCP to fix this problem. So before I tell you how we do it, let me just give you a brief overview of how MPTCP congestion control works. So basically, MPTCP will monitor the loss rates over its subflows, and by using these loss rates, it tries to push away traffic from the paths that have high loss rates, okay? Now, coming back to our example before, so we had access point 1, which had great wireless bandwidth, and this is what the thick line, the thick gray line shows. And access point 2 had actually poorer wireless bandwidth, and MPTCP had 2 subflows over these 2 access points, okay? And it would measure the 2 loss rates over these 2 access points, and basically, if P2 were higher than P1, MPTCP will actually try to move traffic away from access point 2 to access point 1. However, when you get packet level fairness like we were seeing before, the sender was seeing the same loss rate on both subflows, and it was saying, you know, I think it's fine to use both subflows. And it's, you know, we were getting the results we were seeing earlier. So intuitively, what we want to do is somehow tell the sender, which runs the congestion controller, look, access point 2 is worse, so you should try to avoid it if you can, okay? And for this, the client actually knows which AP is better. So what we have is, we have the client locally estimate which is the better AP. And to do this, the client measures a few indicators. So it looks at the bit rate of packets it receives. It estimates the physical loss rate, and it plugs this in a model of 8.11 we have built. And what this model gives you is this thing we call packet time. So basically, it gives you the estimated time needed to deliver a packet, including the retransmissions, okay? So the client has a packet time for all the access points it's connecting to. And then basically, whenever some access point is 30% worse than the best access point that the client is connected to, the client starts telling the server, look, you should avoid this access point. So how does it do this? Well, the easiest thing to do would be to just drop packets received from access point 2, but obviously that's not work conserving, so it's not nice. What we do instead is we use ECN. So basically, the client will mark packets received by AP2, will mark a percentage of them with the ECN congestion experience code point. This happens in the driver before they are passed up to the TCP stack, and the TCP stack implementation of ECN will make sure that this is conveyed to the sender. So you could say mark 10% of the incoming packets, and the effect is that, you know, all of a sudden P2 looks so much higher to the sender that the sender will actually push all of the traffic away from access point 2 to access point 1. However, if you do this blindly, like in this example, you can also run into trouble. Say access point 1, you know, has great wireless bandwidth, but it also has a bottlenecked uplink, okay? In this case, if you just blindly mark 10% like we did, the only effect you get is you're actually reducing your total throughput, okay? So in this particular case, you move traffic away from access point 2, but you can't really put it on access point 1 because access point 1 has a very bad uplink, okay? So the takeaway here is, look, it's fine if you want to mark, but you can't just mark with a very high rate because you might decrease your throughput in certain scenarios. So what we really need to do is to select an appropriate marking rate. And To understand what's a good marking rate, we're going back to the design of the MPTCP congestion controller. So basically, MPTCP has another goal that says you need to do at least as good as TCP on any of the paths, okay? So MPTCP will look at all of its subflows and try to estimate, based on RTT and loss rate it sees, it will try to estimate what would TCP get on this path. And it will try to match that particular throughput in aggregate. So if TCP gives you 10 megabits on this path, MPTCP tries to give you at least 10 megabits over all of its paths, right? So it tries to get the max of all subflows, okay? So basically, to solve the problem we were seeing earlier, we just need to understand how MPTCP estimates throughput for the bad access point, okay? And it estimates throughput according to this very simple throughput formula. You know, it doesn't really matter. So basically, what we're doing is when you're actually marking delta packets as congested, the effect on the throughput of access point 2 is going to be that you're decreasing the congestion window and you're decreasing the RTT as an effect, okay? So now, to make sure that we don't skew MPTCP's perception of throughput via access point 2, what we want to do is to ensure that this formula holds. So we're saying, look, access point 2 is bad at this point, but the throughput you're getting now should be the same, or the throughput estimate you're getting now should be the same throughput estimate after marking, okay? And this is shown by this formula. So if this formula holds, then the marking algorithm is completely safe, okay? And basically, I won't go into the details, but what I can tell you is that we have a way to compute this delta, this marking threshold, in a closed form. So the client can compute this delta for every access point and for every connection. And as long as it adheres to this, it should be no problem. So it shouldn't actually get less throughput by marking. We've implemented this in the device-independent part of the Linux kernel, and we actually tested it. So this is a very simple experiment. In blue, you have MPTCP without marking. And what you see is that without marking, you basically drop 30 to 40% of the throughput. When you do marking, you actually get 80 to 90% of the performance, of the optimal performance, okay? This is all good, so it is actually working. It's managing to mark in the case it's supposed to work. The question is, when you have a bottleneck at the access point, is it still working? Okay. For this, we ran another experiment where we said, look, we have two access points. Access point 1 gives you really bad performance, and but it's 5 megabits. So this is the performance you'd get if you ran TCP via access point 1. Access point 2 gives you performance that depends on the number of TCP connections to the bottleneck link. And this is what we vary. Okay, so on the x-axis, I have the number of contending traffic on the uplink of the access point. And this is what you would get if you ran TCP via access point 2. If you have no contending traffic, you get 25 megabits, which is the optimal for 11A. If you have one connection, you get 10, and so forth. Okay? So as you see, with MPTCP, without marking, you basically always get at least as good as TCP via access point 2, but you have an area from 0 to 4 connections where you're actually getting a lot less throughput than you should get. Okay? Now, with ECN marking, what you see is that you get the best of both worlds. Okay? So when access point 2 actually offers better throughput, you get that throughput. When access point 1 is better than access point 2, you also get that throughput. And this is because the marking algorithm works correctly. So I'd like to wrap up this presentation by showing you a real mobility trace. So this is, in our building, a walk from our office to the cafeteria. We'll show you these access points. There are 3 access points. What I'm showing you is throughput of TCP if you connect to only one of these access points. So what you see here is that we basically have 3 different mountains of throughput. And in theory, a client moving from our office to the cafeteria should be able to get a true mobile experience. Okay? The first thing we tried is to do a handover implementation. So we basically used multipath TCP to do a very simple handover implementation where the client monitors the number of beacons it receives from the current access point it's connected to. And when the number of beacons drops under a certain threshold, it basically switches to another access point. And this is the throughput you would get with this solution. So basically, it works pretty much well, except for the areas in between access points when you actually get a drop in throughput. And this drop depends, the exact position of this drop depends on the actual threshold we use to decide when to move. But I'll just tell you that we played with many thresholds, and basically this is as good as it gets. Okay? Now, if you do multipath TCP, this is the throughput you get. And basically, what you can say is, that it's actually very, very close to optimal. Okay? So I'll finish by saying that, MPTCP and Wi-Fi is really love. It works really, really well for hidden terminals, so it basically just works out of the box. And it works very well in carrier sense when all senders use the same rate, or when you use really aggressive congestion rate control algorithms that prefer high rates despite high physical loss rates. And you do need to intervene in certain cases, and this is what we did with our ECN marking algorithm. And have a look at the paper. So we ran extensive simulations that basically try out this solution across a wide range of cases. Finally, the code is available, so we're still working on it, but you can download it and play with it. And with that, I'll take questions. Thank you.
Hey, so I was wondering, the losses, I just skimmed through the paper and I didn't see, are you looking at the frame losses before retransmissions? Like, are you peering into the MAC layer to see if there is a retransmission when you're looking at frame losses?
So are you asking how we estimate loss of physical transmission?
Yeah, is it like a loss as in like a TCP loss where,
No, this is, so the client estimates physical delivery ratio, and basically the way we do it is by looking at the retry bit in the MAC header.
Cool, okay.
And so we're estimating the delivery ratio for only the first transmissions of every packet by looking at the retry bit.
Got it. So
and
you're looking at a trace of the packets that were sent? Okay, got it.
I mean, it's done in real time, it's not a trace. I mean,
understood.
You just, and I mean, let me just show you a graph, because
yeah.
I was expecting this question. So basically, this is how you perform. Gray is the ground truth, and
okay.
dark is the client estimate. So it's pretty close to the ground truth. Yeah.
Thanks.
So a more general question: wouldn't you want to look at sort of inter-arrival times of packets on different subflows in MPTCP, because the differences in those essentially give you finer-grained information about relative congestion of paths, making it more accurate as to how you shift load? Because right now you are relying on coarse-grained estimates of loss rates and RTTs and things like that.
So the question is, why don't we use timing information on different subflows to do more accurate congestion control? I mean, that's a good point. The thing is, you have so many confounding factors that can affect packet timings that it's really difficult to have a reliable signal there. I mean, you could have a bottleneck in the uplink of the access point. You could have a bottleneck on the wireless link, and so forth. So it's kind of difficult. I mean, the server can be anywhere. It doesn't have to be very close to the access point.
I was talking about inter-arrival time. So you basically, at the local receiver,
Mm-hmm.
you get the hardware these days supports very accurate timestamps.
Right.
Basically timestamp each received packet on the subflow, and you get a sequence of inter-arrival times on one subflow, a sequence of inter-arrival times.
So the problem is, if you just look at inter-arrival times, you need to distinguish between two cases. The case where, so the variability could be because you have different transmissions per packet and different bit rates and so forth. Or the variability could come because your AP is not sending because it's carrier sensing and shutting up for some other access points. So you can't really tell which is the case, right? Especially when you're in carrier sense, basically the two guys are fighting out with each other. So you can't really use packet timing. It depends on the rate control algorithm, the outcome. So it's not really a good indicator. So I mean, it could be that you have this inversion problem where if you have a really, if someone sends, let's say, at 2 megabits, but never loses a single packet, and the other one sends at 54 and loses 10%, basically the 2 megabit guy will actually win the contention a lot more times. So it's even worse, right? So it's because you're in carrier sense and the two guys are affecting each other, you can't really use packet timings like that.
Any other questions? Okay, let's thank the speakers on the session.
Thank you.